Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to be tackling a practice problem set that relates to our lecture on kinematics and dynamics. Let's go ahead and get started with problem 1. Problem 1 says a person walks 30 meters east and then 40 meters north. What is the difference between the travel distance and the displacement? Now, to solve this problem, we need to carefully distinguish between the concepts of distance traveled and displacement, and then determine the difference between the two. Distance traveled is going to be the total length of the path that the person walks. So in this case, the person walks 30 meters east and then 40 meters north. To find the total distance, we simply add these two distances together. 30 meters plus 40 meters gives us a total of 70 meters. So the total distance traveled by the person is 70 meters. Displacement, on the other hand, this is a vector quantity that refers to the shortest straight line distance from the starting point to the final position along with the direction. To calculate the displacement, we need to find the magnitude of the resultant vector formed by the eastward and northward movements. So the person's movement actually forms a right triangle where one leg is our 30 meters east and the other leg is our 40 meters north. The displacement is going to correspond to the hypotenuse of this right triangle. Now we need to calculate the length of the hypotenuse using the Pythagorean theorem. So here, displacement is going to be equal to the square root of 30 meters squared plus 40 meters squared. Now, if we carry this out, it's going to be equal to the square root of 900 plus 1600, and that's going to give us the square root of 2500, and the square root of 2500 meters squared is just going to equal 50 meters. So, our displacement is equal to 50 meters. And this is 50 meters in a direction northeast from the starting point. Now the problem, it asks for the difference between the travel distance and the displacement. In order to do that, we're going to have to subtract 70 meters minus 50 meters. That gives us 20 meters. This is our difference between the distance traveled and the displacement, and that corresponds to answer choice B. So problem 1 is B. Let's move to problem 2. This second problem says a 1,000 kilogram rocket ship traveling at 100 meters per second is acted upon by an average force of 20 kilonewtons applied in the direction of its motion for 8 seconds. What is the change in velocity of the rocket? Now, to solve this problem, we're going to need to determine the change in velocity of this rocket when acted upon by a given force over a certain period. The first thing we want to do is write down what information we're given in this problem. Then we want to write down what we're trying to figure out. And then we're going to write down all the relevant equations we could possibly use to calculate our desired quantity. Now, in this problem, we know the mass of the rocket, it's 1,000 kilograms. We know the force, it's 20 kilonewtons, in other words, 20,000 newtons. The time is 8 seconds, and the initial velocity is 100 meters per second. Now, our goal is to figure out the change in velocity, delta V. That's our goal. Let's go ahead and keep that in mind and write down any relevant equations we can use here. Now, velocity, change in velocity, is defined as change in displacement over change in time. While we know the change in time, we're not given any information where we could work backwards and obtain the change in displacement. Another equation that has delta V, change in velocity, within the equation is our definition for change in acceleration. Change in acceleration is equal to change in velocity over change in time. So if we wanted to solve for change in velocity, we can rearrange this expression to be equal to change in acceleration multiplied by change in time. Now, it's important to note that we're not directly given change in acceleration. However, we are given just enough information to figure it out. And the way that we can figure this out is by using Newton's second law. Newton's second law says that force is equal to mass multiplied by acceleration. We have force and we have mass. We can rearrange this expression to solve for acceleration. Acceleration is going to be equal to force divided by mass. And we can take this term and plug it into here to solve for change in velocity. So now our expression for change in velocity, that's going to be equal to force divided by mass multiplied by change in time. And we know all three of these variables, so we can go ahead and plug them into our equation. Force is 20,000 newtons. Mass is 1,000 kilograms. Now, if we were to simplify this part, this would just be equal to 20 meters per second squared. And then we can't forget to multiply by delta t, our change in time, which is 8 seconds. So what we have here is 20 meters per second squared multiplied by 8 seconds. 20 times 8 is 160, and then these seconds cancel out, so our units is meters per second. Our change in velocity is going to be 160 meters per second, and that's going to be answer choice A. Beautiful. Let's tackle problem 3 next. This problem says a car is traveling at 40 kilometers per hour, and the driver puts on the brakes, bringing the car to rest in a time of 6 seconds. What is the magnitude of the average acceleration of the car? Now, the first thing we need to do is recognize that acceleration is defined as the change in velocity divided by the time interval over which the change occurs. Now, to solve for delta V, change in velocity, we need to keep in mind that the car's initial velocity is 40 kilometers per hour, and because it comes to a complete stop, the final velocity is 0 kilometers per hour. That means we can calculate the change in velocity as final velocity minus initial velocity. That's going to be 0 minus 40. That gives us a change in velocity equal to negative 40 kilometers per hour. And that negative sign indicates that the car is decelerating. Now, what about delta t? We're given the change in time within the question stem. We're told it takes 6 seconds to bring the car to a complete stop. The problem is that our change in velocity is in units of kilometer per hour, and our delta t is in units of second. We want to go ahead and convert this to units of hours so that we can do the division appropriately and have the appropriate units cancel out. So to do this, we're just going to use a little bit of dimensional analysis. 1 hour is equal to 3,600 seconds. This is going to be equal to 6 divided by 3,600. And if we divide the numerator and denominator by 6, we get 1 over 600 hours. So 6 seconds is equal to 1 over 600 hours. And now we can go ahead and plug it into our expression for acceleration. Change in acceleration is equal to negative 40 kilometers per hour divided by 1 over 600 hours. Now, really quickly, let's focus on the units here. We have kilometers per hour, and then we're dividing by hours. So our final units are going to be kilometer per hour squared. Okay, so that's our units, kilometer per hour squared. Now let's focus on the math. In the numerator, we have negative 40, and then we're dividing that by 1 over 600. In other words, we're multiplying by 600. So negative 40 multiplied by 600 is going to be equal to negative 24,000, and our units are kilometer per hour squared. 24,000, negative 24,000 kilometers per hour squared. Now, in the problem, we're asked for magnitude, which means we're going to take the absolute value of this, and that gives us 24,000 kilometers per hour squared. And that best aligns with answer choice C. So 3 is C. Let's do problem 4 next. Problem 4 says an elevator is designed to carry a maximum weight of 9,800 newtons, including its own weight, and to move upward at a speed of 5 meters per second after an initial period of acceleration. What is the relationship between the maximum tension in the elevator cable and the maximum weight of the elevator while the elevator is accelerating upward? So to solve this problem, we're going to need to analyze the forces acting on the elevator as it accelerates upward. And here, there are 2 key forces at play. First, we have our gravitational force. This is the force pulling the elevator downward, and it equals the weight of the elevator. And then we have our tension force. This is the force exerted by the elevator cable to pull the elevator upward. This force has to counteract the gravitational force, and it needs to provide additional force to accelerate the elevator upward. Now, when the elevator is stationary or moving at a constant speed, the tension in the cable would exactly balance the gravitational force. That means that the tension force is equal to the gravitational force, and that is going to be equal to 9,800 newtons. Remember, the gravitational force is the force pulling the elevator downward, and it's equal to the weight of the elevator, which we're given as 9,800 newtons. Now, the problem is specifying that the elevator is accelerating upward. This statement is true when the elevator is stationary or moving at a constant speed. So in the case that the elevator is actually accelerating upward, we need to think a little bit differently. In this case, the tension in the cable must not only balance the gravitational force, but it also provides the extra force necessary to accelerate the elevator upward. Now, according to Newton's second law, the net force acting on the elevator during its upward acceleration, that's going to be equal to mass multiplied by acceleration. The tension in the cable must overcome both the gravitational force and then provide the additional force for acceleration. Therefore, the total tension in the cable is going to be the sum of the force required to counteract gravity and the force required to accelerate the elevator, plus ma. So again, let me repeat. When the elevator is stationary or moving at a constant speed, the tension in the cable would exactly balance the gravitational force. However, when the elevator is accelerating upward, the total tension in the cable is the sum of the force required to counteract gravity and the force required to accelerate the elevator. Now, we know that the force of gravity is equal to 9,800 newtons. So we're going to write that down. And ma, mass times acceleration, this is going to be a positive value because the elevator is accelerating upward. That means that the force, the tension force, it's gonna have to be greater than 9,800 units. We're not gonna be able to calculate the exact value because we don't have enough information, but we're given just enough information to know that because the elevator is accelerating upward and we know the force of gravity is equal to 9,800 newtons, the force, the tension force, is going to be greater than 9,800 newtons. And that means that the correct answer for problem 4 is going to be A. The tension is greater than 9,800 newtons. Let's tackle problem 5 next. Problem 5 says a student must lift a mass of 4 kilograms, a distance of 0.5 meters. The ambient temperature is 298 Kelvin, and the student must lift the mass in 30 seconds. Which of the following values is not necessary to calculate power? Our answer choices include mass, distance, temperature, and time. Now, I want to point out that the concepts you need to answer this problem, they were not covered in Chapter 1. They will actually be covered in Chapter 2. I don't know why Kaplan does this, but regardless, I'm going to provide you with the background information you need to solve this problem, and we're going to start by defining power. Power is the rate at which work is done, and it's mathematically expressed in this way. Power is equal to work divided by change in time. Now, this work term we can redefine. The work done in lifting an object is calculated as the product of the force applied and the distance the object is moved. We can write this as force multiplied by displacement multiplied by cosine theta, where theta is the angle between the force vector and the displacement vector. So now we have power is equal to force multiplied by displacement multiplied by cosine theta, and that's all divided by change in time. Now we can rewrite the force term as well using Newton's second law. Force is equal to mass times acceleration, so we're going to substitute that term in for force. Now our definition for power is mass times acceleration times displacement multiplied by cosine theta, and that's all divided by change in time. We notice we have a mass term, we have a distance term, and we have a time term, but we do not have a temperature term. And actually, the correct answer for problem 5 is answer choice C. We do not need temperature to calculate power. Alternatively, you can write the units for power and answer this problem based off of that. The unit for power is the watt, and this is expressed as kilogram times meter squared in the numerator, and then in the denominator you have seconds cubed. Kilogram is the SI unit for mass, meter is the SI unit for distance, and second is the SI unit for time. And so just from the units of power, you can determine that you need mass, distance, and time to calculate power, but you do not need temperature. And that's why the answer to problem 5 is answer choice C. Let's go ahead and move into problem 6. Problem 6 says, a firefighter jumps horizontally from a burning building with an initial speed of 1.5 meters per second. At what time is the angle between the firefighter's velocity and acceleration vectors the greatest? A says the instant the firefighter jumps, B says when the firefighter reaches terminal velocity, C says halfway through the firefighter's fall, and D says right before the firefighter lands on the ground. Now, when the firefighter jumps, the initial velocity is entirely horizontal, and there's no vertical component to the velocity. However, gravity immediately begins to accelerate the firefighter downward, introducing a vertical component to the velocity that increases over time. Now, the acceleration vector, it is always directed downward due to gravity, and it doesn't change direction or magnitude throughout the fall. The velocity vector, however, it begins to change over time. The velocity vector begins purely horizontal, and then it gradually gains a downward component as the firefighter falls, causing the vector to rotate downward. Now, the angle between the velocity and acceleration vectors is greatest when the velocity has the smallest vertical component relative to the horizontal component. And that occurs at the very beginning of the jump when the velocity is entirely horizontal. At this moment, the velocity vector is perpendicular to the acceleration vector. Let me repeat this. At this moment, when the firefighter first jumps, the velocity vector is perpendicular to the acceleration vector, forming a 90-degree angle, which is the maximum possible angle between the two vectors. Now, as the firefighter continues to fall, the vertical component of the velocity increases and it reduces the angle between the velocity and the acceleration vectors. By the time the firefighter reaches the ground, actually, the velocity vector is nearly aligned with the acceleration vector, making the angle between them very small. So, in conclusion, the angle between the firefighter's velocity and acceleration vectors is greatest at the instant that the firefighter jumps, and this corresponds to answer choice A. Let's do problem 7 next. Problem 7 says a 10-kilogram wagon rests on an inclined plane. The plane makes an angle of 30 degrees with the horizontal. Approximately how large is the force required to keep the wagon from sliding down the plane? And here we're given the value for sine 30 degrees and cosine 30 degrees. Now, the first thing we want to do is sketch out a diagram that represents what this problem is describing. So here we have our inclined plane, makes a 30-degree angle with the horizontal, and here we've drawn our wagon. Now, the second step we want to do is identify the forces acting on this wagon. The first force we have is going to be our gravitational force, which acts downward. This is the weight of the wagon, so it's acting vertically downward. So it's going to be the product of the wagon's mass and the acceleration due to gravity. Then, the second force that's acting on this wagon is the normal force. This is the force exerted by the surface of the inclined plane, and it acts perpendicular to the plane. It counteracts the perpendicular component of the gravitational force, preventing the wagon from accelerating through the surface. Then our third force is going to be our static friction force. This is the force that opposes the motion of the wagon, preventing it from sliding down the incline. In this case, static friction is acting up the plane to oppose the gravitational force that tries to pull the wagon down the plane. Now, I've taken these forces and I've drawn it in a more concise way that it looks like a free body diagram. So this purple dot signals our wagon, and here we've drawn our three forces that act on the wagon: our force of gravity, our normal force, and our static friction force. Now, for our static friction force, for our normal force, for our force of gravity, we can define a coordinate plane. And then according to what we define as our coordinate plane, we can break down some of these forces into their x and y component. Now, while these three forces are acting on the wagon, we're going to be primarily interested in the gravitational force because it is the component of gravity parallel to the incline that's going to try to move the wagon downward. So what we're going to do is we're going to define our XY plane to look something like this. All right, here's our coordinate plane. We're going to define this as the x-axis, and this is the y-axis. Yes, you typically see it drawn like this, but we're going to redefine our coordinate plane. And what we notice is our force of gravity is the only one that's not directly on the x-axis or just on the y-axis. It has both a x and a y component that we're going to call our parallel and our perpendicular component. So we're going to resolve the gravitational force into its parallel and perpendicular component. Now, when we do that, I'm going to go ahead and erase this coordinate plane so it's not getting in the way of us drawing our parallel component of gravity and our perpendicular component of gravity. So this is our parallel component of gravity, and this is our perpendicular component of gravity. And again, I want to say that we're primarily interested in the gravitational force because it is the component of gravity parallel to the incline that's trying to move the wagon downward. Of course, the static friction force will oppose this gravitational component, and to find the necessary static friction force, we need to break the gravitational force into its two components. So now that we understand that, we can go ahead and start to calculate our parallel component for our force of gravity. This is defined as Fg sine theta. And our perpendicular component is defined as Fg cosine theta. Now, to calculate our gravitational force, this is just equal to mass times acceleration, and specifically the acceleration due to gravity. We have our mass, it's 10 kilograms, and our acceleration due to gravity is 9.8 meters per second squared. So this gives us a total of 98 newtons. So now that we know that, we can go ahead and plug it into our equations. So our parallel component is going to be 98 newtons multiplied by sine theta, sine 30 degrees, which we're given in the problem. It's equal to 0.5. So when we calculate this, we're going to get 49 newtons. The parallel component for our gravitational force is 49 newtons. Then we can carry out the same calculation for the perpendicular component. It's going to be 98 newtons multiplied by cosine theta. So this is cosine 30 degrees, which is equal to 0.866. This is going to give us approximately 85 newtons. Now that we have our parallel and perpendicular component, we can start to think about this problem. To prevent the wagon from sliding down, the static friction force has to be equal to our parallel component of our gravitational force. If our static friction is equal to the parallel component of gravity, then the wagon doesn't move. And that is what this problem is asking us. Approximately how large is the force required to keep the wagon from sliding down the plane? The static force has to equal the parallel component of our gravitational force for that to be true. And we just calculated that the parallel component of our gravitational force is equal to 49 newtons. That means that the static friction force required to keep the wagon from sliding down the incline is 49 newtons. And that's going to correspond to answer choice B. So 7 is B. Let's move on to problem 8. Problem 8 asks, which of the following expressions correctly illustrates the SI base units for each of the variables in the formula below? We have mass multiplied by change in velocity. It equals force multiplied by change in time. Okay, let's break down the SI units for each term. For mass, The SI unit for mass is the kilogram. What about for change in velocity? Velocity has units of meters per second. Now, this is equal to force. Force is measured in newtons, and the newton is defined as the force required to accelerate a 1 kilogram mass by 1 meter per second squared. So we want to write newton in its SI units. So it's going to be 1 kilogram multiplied by meter over seconds squared. And then change in time. Time is measured in seconds. So looking at our answer choices, the one that best aligns with what we wrote is going to be answer choice C. Notice kilograms for mass, meters per second for change in velocity, kilograms multiplied by meters over second squared for force, and then second for time. So again, the correct answer for 8 is answer choice C. And with that, we'll move into problem 9. Problem 9 says, the diagram below shows two vectors. If a student uses the formula AB sine theta, where A and B are the magnitudes of the respective vectors A and B, then which of the following best describes the computed value? Now this expression, AB sine theta, this is used to calculate the magnitude of the cross product of two vectors. The cross product of two vectors A and B is a vector that's perpendicular to the plane containing A and B, and it's equal to AB sine theta, where here theta is equal to 60 degrees. Now the direction of the cross product vector, it's going to follow the right hand rule. So take your right hand, you want your pointer finger and your middle finger to align with vector A and B respectively. So what this is going to actually look like is you're going to have your palm point up, your pointer finger is going to follow vector A, your middle finger is going to follow vector B, and your thumb is going to point in the direction of the resulting cross product vector, which you realize it's pointing upwards. So that means the vector is out of the page, and the correct answer for problem 9 is going to be answer choice D. Wonderful. Next up, problem 10. Problem 10 says which of the following quantities is not a vector? Option A says velocity. Now, velocity is a vector because it describes both the speed of an object and the direction in which the object is moving. B says force. Force is also a vector because it represents the magnitude of the push or pull and the direction in which it acts. So we're also going to eliminate B. C says displacement. Displacement is also a vector because it describes the shortest path between two specific points in a specific direction. So we'll eliminate answer choice C as well. Answer choice D says distance. Distance is a scalar quantity because it only measures how much ground an object has covered without considering direction. So it represents the total path length traveled. So given this analysis, distance, option D, is going to be the quantity that is not a vector. So the correct answer for question 10 is D. Let's tackle problem 11 next. Problem 11 says a 30-kilogram child sits on a seesaw at a distance of 2 meters from the fulcrum. Where must the child's parent sit to balance the seesaw if the parent has a mass of 90 kilograms? Now, for the seesaw to be balanced, the torques around the fulcrum have to be equal. So we can say that the torque due to the child has to be equal to that due by the parent. Now we can expand our torque term. Our torque is equal to the force multiplied by the distance from the pivot. So this would be the distance from the fulcrum in this problem, multiplied by sine theta, where theta is the angle between the force vector and the lever arm. And we can expand this for both sides, for the torque due to the child and that due to the parent. Now that we have this written, I want to say that we can go ahead and omit this sine theta term for this problem. Why? Well, here, sine theta, theta is going to be the angle between the force, which is gravity acting downward, and the lever arm, which is the distance along the seesaw. That theta between those two is going to be 90 degrees, and sine 90 is equal to 1. So this term is omitted because it's just equal to 1. So what we have here is the force of the child multiplied by the distance of the child from the fulcrum. And that's going to be equal to the force caused by the parent, the force of the parent, multiplied by the distance from the fulcrum that the parent sits. Okay? So in other words, this is what we're trying to solve right here. We can calculate this force term because it's just going to be equal to the weight of the child. It's just going to be equal to 30 kilograms, that's the weight of the child, multiplied by the acceleration due to gravity, which we're going to round as 10 meters per second squared. And the child is sitting 2 meters from the fulcrum, so that's going to be that R term right here. This is going to be equal to the force of the parent. This is the weight of the parent, 90 kilograms, multiplied by the acceleration due to gravity, which is 10 meters per second squared. And then this RP term is what we're trying to figure out. We're trying to figure out the distance from the fulcrum that the parent has to sit for the seesaw to be balanced. So let's go ahead and try to calculate this out. Now, both sides have this 10 meters per second squared, this acceleration due to gravity. We're just going to cancel those terms to make the math a little bit easier. Then we're going to move 90 kilograms over to the other side. So we're going to divide both sides by 90 kilograms so that we can isolate this term and solve for it. This is going to be equal to 30 kilograms multiplied by 2 meters divided by 90 kilograms. Now here the units kilograms cancel out. We're going to get our final answer in units of meter. And this is going to be 60 over 90, which can be simplified as 6 over 9, which can be further simplified to 2 over 3 meters. This is approximately equal to 0.667 meters, or this is also equal to 66.7 centimeters. So that is our answer. So looking at our answer choices, we're looking for an answer that says the parent sits 67 centimeters away from the fulcrum. That best aligns with answer choice B. So the correct answer for problem 11 is B. Let's move on to the next problem. Problem 12 says a physics major builds a potato launcher and tests it in an open field. The student launches a potato with a velocity of 12 meters per second at an angle of 30 degrees. The potato is found 60 meters from the launch site. Which of the following represents the maximum height achieved by the potato? And note that sine 30 degrees is equal to 0.5. Now, when we're solving projectile motion problems, it's helpful to break the velocity into two components, the horizontal and the vertical component. So let's go ahead and write our equations for both components. For our horizontal component, our initial velocity for that horizontal component, that's going to be equal to v cosine theta. For our vertical component, that's going to be equal to v sine theta. Now, since our ultimate goal for this problem is to find the maximum height, we only care about the vertical motion. So we're just going to solve for this component. This is going to be equal to v, which is 12 meters per second, multiplied by sine theta, where theta is equal to 30 degrees. And we're given what sine 30 degrees is equal to. It's equal to 0.5. So now we have 12 multiplied by 0.5. This is going to be equal to 6 meters per second. Now again, We want to find the maximum height. We only care about the vertical motion. And the idea is that at the highest point, the potato's vertical velocity becomes 0, and we can use the following kinematic equation. Vy squared is equal to Vy naught squared minus 2gh. This Vy squared, this is our final velocity at the top. This is equal to 0. So this is going to be 0 meters per second squared. This is just going to equal 0. Then this term right here, Vy naught, this is the initial vertical velocity that we just calculated as 6 meters per second. This is going to be squared, and that gives us 36 meters squared per second squared, minus 2g. G is the acceleration due to gravity, which we're going to approximate as 10 meters per second squared, and h is the maximum height we're solving for. So in order to solve for h, we want to isolate that variable. The first thing that we can do is we can move this term to the other side. So what that's going to give us is 2 times 10, that's equal to 20 meters per second squared h, and this is equal to 36 meters squared per second squared. Again, we just want to solve for h, so what we're going to do is we're going to divide both sides by 20. All right, we're going to divide both sides by 20. This is going to give us that h is equal to approximately 1.8 meters. And the correct answer for problem 12 is going to be answer choice B. Wonderful. Let's move on to problem 13. Problem 13 says a rock, mass 2 kilograms, is shot up vertically at the same time that a ball, mass 0.5 kilograms, is projected horizontally. If both start from the same height, blank. A says the rock and ball will reach the ground at the same time. B says the rock will reach the ground first. C says the ball will reach the ground first. And D says the rock and ball will collide in the air before reaching the ground. Now, to answer this question, we only need to analyze the motion in the vertical dimension. If both the rock and ball began with no vertical velocity, they would reach the ground at the same time. However, because the rock begins with an upward component of velocity, it will take time to reach a maximum height before falling back down towards the ground. So functionally, the rock's free fall starts higher and later than the ball's. So the rock will necessarily hit the ground after the ball. And that means the ball will reach the ground first, and the correct answer for 13 is going to be answer choice C. Let's do problem 14. Problem 14 says centrifugal force is an apparent outward force during circular motion. It has been described as a reaction force according to Newton's third law. Which of the following statements is most likely to be correct regarding centrifugal force? Now, centrifugal force is described again as an apparent force that seems to push an object moving in a circular pathway away from the center of rotation. However, it's important to note that this is not a real force. It's a fictitious force that appears in a rotating reference frame. This force is often considered the reaction force to the centripetal force, which is the real force that acts towards the center of the circular path, keeping the object in motion. Keeping that in mind, let's analyze each statement. Statement A says centrifugal force exists only for uniform circular motion, not non-uniform circular motion. Now, this statement is incorrect because centrifugal force can be perceived in any rotating reference frame, regardless of whether the circular motion is uniform or non-uniform. Now, statement B says centrifugal force exists only when tension or a normal force provides centripetal acceleration. Now, this statement is misleading because centrifugal force arises due to the rotation itself, and it doesn't depend on the specific forces providing centripetal acceleration. It can be perceived even if the centripetal force is provided by gravity, friction, or any other means. So B is not the correct answer. C says centrifugal force always acts anti-parallel to the centripetal force vector. Now, this statement is correct. In a rotating reference frame, the centrifugal force is considered to act outward, away from the center, while the centripetal force acts inward, towards the center. Therefore, they are anti-parallel, and actually, answer choice C is the correct answer for problem 14, but we're still gonna talk about statement D here. Statement D says centrifugal force is a result of repulsive electrostatic interactions. This statement is incorrect. Centrifugal force is not related to electrostatic interactions. Remember, it's a fictitious force perceived in rotating frames of reference. So again, the correct answer for problem 14 is going to be answer choice C. With that, we'll move into our last and final problem. Problem 15 says, which of the following statements is true of movement on a plane with friction? Statement 1 says acceleration is a function of applied force only. Now, this statement is incorrect because acceleration is not only a function of the applied force, but also depends on the mass of the object, as per Newton's second law, which states that force is equal to mass multiplied by acceleration. So statement 1 is incorrect. Statement 2 says more force is needed to accelerate a stationary object than an identical moving object. This statement is correct when we're considering static friction versus kinetic friction. Static friction resists the initiation of motion, and it's generally greater than kinetic friction, which opposes the motion of an already moving object. Therefore, it typically requires more force to overcome static friction and start moving a stationary object compared to keeping an identical object in motion. So statement 2 is true. Statement 3 says the force of friction is independent of the mass of objects. This statement is incorrect because the force of friction depends on the normal force, which is proportional to the mass of the object. The greater the mass, the greater the normal force, and consequently, the greater the friction force. So statement 3 is incorrect. The only statement which is true is statement 2. So the correct answer for problem 15 is answer choice B. And with that, we've completed our practice problem set that relates to our chapter on kinematics and dynamics. I hope this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors. I love you all.